Kia ora. I'm Lana from Fulbright, New Zealand, and it is wonderful to have you with us for today's Good Works webinar. It's lovely to see so many Fulbright alumni with us today, and if it is your first Fulbright webinar, a very warm welcome. We are so pleased you have chosen to join us today. For those who are new to Fulbright, we are a part of a global educational exchange program that's been connecting New Zealand and the United States for almost 80 years. Each year, we support students, researchers, academics, and professionals to study, teach, and collaborate in each other's countries. Our Good Works webinar series is one of the ways we highlight the inspiring work of our alumni. We have a range of awards available, and currently our Fulbright New Zealand Scholar Awards are open. So they provide the opportunity to spend 3 to 5 months in the United States undertaking research or lecturing at the universities and other host organizations. New Zealand Scholar Awards are not just for academics. We encourage professionals, artists, and other leaders to apply. It's a fantastic opportunity, so do have a look on our website. Today, we are delighted to welcome Dr. Ribu Dhakal, Assistant Professor of Civil Engineering at the University of British Columbia and a Fulbright alum. Ribu completed his bachelor's and PhD at the University of Canterbury while undertaking a Fulbright scholarship at UC Berkeley. His research focuses on earthquake engineering and improving our understanding of earthquake risk and resilience. Today, he'll share insights from Christchurch and Wellington and explain how science and engineering work together to make our communities safer. We'll have some time for questions at the very end of the presentation, so please feel free to pop in your questions into the Q&A box, and we will come to them at the end. Ribu, thank you so much for joining us. Over to you. I'll stop sharing the presentation.
Great, thank you very much, Lana, for the kind introduction. Please confirm if you can see my screen.
Yes, we can see your screen.
Okay, great. So thanks, Lana, and thanks everyone for joining during lunch hour for those in New Zealand and other hours for those that are perhaps joining from Canada or elsewhere. So today I'll be talking about primarily living with earthquakes, and the title is Building on Uncertain Ground. And the idea here is to kind of debunk some of the myths that we have with regards to earthquakes and maybe get us in the right mindset. And this really stems from my Fulbright experience as well. So from the very beginning, I just want to first acknowledge Fulbright NZ for first inviting me to deliver this talk, but also for the opportunity that it presented. In 2019, I spent my Fulbright at the University of California, Berkeley, where it looks like in the photos I didn't really work hard, but I promise you that I did. And but I also did utilize my time traveling as well, and it was an excellent experience. I made lifelong friends along the way. And so California really holds a special place in my heart, as well as Fulbright and Fulbright NZ as well. And actually, the work that I'll talk about today, while it doesn't necessarily go in depth of my journey, it can actually be traced back to some of the seeds can be traced back to some of my experience of Fulbright. So it really was a great experience there. I also want to thank, a bunch of family, friends, and mentors from the University of Canterbury. I spent about 10 years there as an undergraduate and graduate student, and I also worked there for a couple of years. And so a lot of the work has stemmed from collaboration with them as well. And then finally, some excellent resources that I just want to put up front. So if any of what I talk about today sparks an interest to you and you want to find out more about some of the technical details, these are two great books that I refer to. And in fact, some of the figures in today's talk are from these books as well. The authors, Professor Steve Kramer and Professor Brendan Bradley, have kindly shared with me. So a few acknowledgements there just to come up front. So given the nature of today's talk, I wanted to just preamble for a little bit, just to give us an idea for what we'll be covering today. And today, really, the goal is to get everyone thinking like earthquake engineers. And so naturally, we have the question of, okay, we have built environment, we live in cities, we live in towns with a lot of buildings, a lot of pipes, a lot of infrastructure, and they're exposed to a lot of natural hazards. And so you may be living in a house, and this is obviously just a sketch, and that house at some point may undergo something like this, right? Where you have an earthquake occur, and all of a sudden things are not what we thought they were. And so the goal today is first, in part one of the talk, to really talk about the earthquake hazard. How do we really think about earthquakes as a hazard, and how do we approach them from an engineering perspective? Part two of the talk will then talk about the effects of earthquakes on infrastructure, such as buildings. And so once we have the earthquake hazard kind of philosophy down, we'll talk about how we design for earthquakes for our infrastructure. And then part three, we'll talk about case studies from Christchurch and Wellington, both cities in New Zealand, of course. And like I said, my goal is to get everyone to think more like earthquake engineers. So if you can come out of this talk with a little bit more of an earthquake engineer's brain, then I think I have done my job. So let's see how we do as we go forward in this hour. So with that preamble in mind, this is essentially the table of contents of what I will talk about. So part one is the earthquake hazards, and really we'll be dividing it into four key questions that are often asked, or I get asked very often by my friends and others that are not earthquake engineers, right? Where do earthquakes occur? How big can earthquakes be? How often do they occur? And how far away from the earthquake is it going to affect? Then we'll talk about the effects of earthquakes, the types of damage we might expect, and some of the design principles, right? So next time when you walk into a building, you will understand, hopefully, philosophically at least, the principles that they've designed it by. And then we'll look at the two case histories. One is Christchurch City from the 2010 and 2011 Canterbury earthquake sequence, and then the performance of the Port of Wellington during another earthquake in 2016, but hopefully in reference to some of the principles that we talked about earlier. So let's start with part one, earthquake hazards. Where do earthquakes occur, right? So to understand where earthquakes occur, we need to know what earthquakes are. And if you trace back literature and urban legends, there's a lot of interesting stories about what causes earthquakes. So in New Zealand, the Maori god of earthquakes, Ramoko, was said to reside within the womb of its earth mother, Papatuanuku. And apparently when his movements in the womb became restless, that was an earthquake. Right, that's what they used to believe. Or in Japan, a giant catfish named Namazu lives under the islands of Japan, and the thrashing of the catfish causes earthquakes. You can see here the drawn in black here, the catfish. And when another god uses a rock to keep it in place, it's okay. But every now and then it thrashes about and it causes earthquakes. And you have similar stories of a frog in Chinese folklore and elephants in India. So you know, there's a lot of different stories around, and it's always been kind of part of human curiosity to think about what causes earthquakes. But of course, we know more recently that it's a result of movements of tectonic plates. So we know that the Earth is made up of a bunch of different layers: the inner core, the outer core, the mantle, and the crust. And if we look at this image on the bottom here, it kind of gives you an idea for the relative thicknesses of these different layers. And you can see the crust layer is really thin in comparison to the rest. So it kind of sits on top of this kind of fluid-like bed. And this allows this crust to kind of move around depending on the movement of the layer underneath. And so the image on the right kind of illustrates that, where the crust can be pulled and pushed in different directions based on convection currents and flows of the magma underneath the ground. And so naturally, when the crust portions move in opposite directions or adjacent directions, naturally we're going to have some interaction and therefore some energy release. And that's essentially the cause of earthquakes. Now, how do we know this is occurring in the Earth's crust? Well, we don't need to look any further than the historical maps of Earth. So we know Pangaea was what Earth looked like back in the day. And then over the several hundreds of millions of years, this is what the world looks like today. And this is all a result of these continental drifts, right? Evidence of the fact that the crust does indeed move around, albeit very slowly. We're not going to see it in our lifetime, but over several hundred millions of years, it is very, very obvious. And so the movements are generally divided into 7 tectonic plates. So this is a world map. And these lines are demarking where these plates are. So you can see the South American plate, North American plate, the big Pacific plate here, which causes forms the ring of fire that we've heard about, Indian and Australian plates, Antarctic, African, Eurasian. And so it's unsurprising to find that actually movements of these plates along these boundaries, you can see these arrows showing relative movement of these plates, can be in opposite directions. And when you have movements of 2 adjacent kind of solid structures in opposite directions, naturally there's going to be energy releases. And that's essentially where earthquakes occur. And so if we have a look at a map of where all earthquakes have occurred in recent history, or at least measured and recorded history, unsurprisingly, they occur along these plate boundaries for the most part, right? So these lines here are showing you where those plate boundaries exist, and the dots are showing you where the earthquakes have been observed. The larger the size of the dots, the larger the earthquakes are. And so naturally, we would expect them to be concentrated in and around these lines. Of course, you do get some intra-slab events every now and then, and these are unique cases, but by and large, that's what we're seeing. So we're seeing earthquakes. Where do they occur? Well, primarily near the boundaries of these large tectonic plates. And there's many hotspots for earthquakes in many well-known cities. 3 cities in particular that have, or 3 areas, let's say, not necessarily cities, that have a particular important place in my heart. Of course, New Zealand, as everyone, many people may know, sits along a plate boundary as well. And so unsurprisingly, we should expect earthquakes at some point in New Zealand. I now have moved to Vancouver, and this is where I reside. And Vancouver also has been inundated with earthquake hazards in its past as well. And my home country of Nepal as well, or my ancestral country of Nepal, also has recently seen earthquakes, especially the 2015 Gorkha earthquake. And so Nepal is also in an area where there's earthquakes. So definitely, at least personally for me, a very important natural hazard that I deal with constantly. And of course, many of you may be following the news and knowing about many earthquakes that have been occurring in 2026. So for example, and these are just 4 I listed based on kind of the impact they had and perhaps impacts on people. So the Philippines earthquake, magnitude 7.8. We had, of course, the Venezuela, what we call the twin events. And then even more recently, in fact, this was only 3 days ago in Colombia as well. And then we had one very recently again in Japan, and there's been plenty of others, Indonesia, etc. And again, like I said, it's unsurprising that the locations they're occurring are along plate boundaries. So while we may comment on the fact that, okay, they're occurring at kind of close intervals, but the locations that they're occurring at is not surprising, given the fact we know that they're along plate boundaries. So just to highlight kind of where we should be expecting earthquakes. Now, of course, plate tectonics can interact in a variety of complex ways. So, 2 plates could be diverging, they could be converging with each other, and therefore causes these subduction zones. And often this is where Alps and mountain ranges are formed as well. We could have a transform plate boundary where they move kind of adjacent to each other. And the way they interact will then cause different types of earthquakes, different types of shakings, different magnitudes. So it's a very complex phenomena, and it's not always easy to capture, as you would imagine, given it's several tens of kilometers or sometimes hundreds of kilometers into the ground. But of course, we have evidence of fault movement that can be seen in the ground surface sometimes. So on the left is an image following the Kaikoura earthquake in 2016, and we can clearly see the fault rupture kind of manifesting on the ground surface. Even though it would have started, tens of kilometers deep, you can kind of sometimes see it on the ground surface as well. So here, for reference, there are 2 people, they're doing some surveys. So we're seeing displacements in the order of several meters along this fault here. And then on the right is kind of an aerial view showing you surface manifestation of the San Andreas fault. So we can see the surface effects as well from that fault movement. So indeed, we have we can see it on the ground, but we often use kind of ground tomography to further quantify these types of movements. So now the next question is, how big can earthquakes be? Well, that's not a straightforward question to answer. Earthquake strength is often measured based on the energy released, and just a big disclaimer, this is the only slide I have with an equation. So if you don't like equations, bear with me for one slide, and then I promise you there'll be no more. But we often use this equation here, which we refer to as the seismic moment. And essentially, it's an equation that considers two factors. One is the area of the rupture, and the other is the slip distance itself. So how big is the actual rupture area that we're seeing, the interaction area between two faults, and how much displacement has occurred? And the larger the displacement, the larger the energy released, and the larger the area, again, also larger the energy released. But of course, seismic moment can lead to some funky numbers, and so we often normalize that and use other values. But the first thing to note is that naturally now we can see that the area of the fault rupture therefore forms an upper bound on the energy released. Right? If there's a certain area of overlap between two faults, that naturally forms an upper bound on the amount of energy that can be released. That is why we often hear about, for example, the Alpine fault earthquake can cause up to a magnitude 8, because we know the area of that rupture and we know it can't be any bigger than that, compared to, say, Chile, where we know it can get up to 9.5. Okay? However, we often convert this moment magnitude, seismic moment, to what we call a moment magnitude. And so again, it's just an equation that converts one value to another, but the key in this equation is actually this log term. And those of you that can recall your maybe high school mathematics, a log term essentially means that an increase in magnitude by 1 means there's 10 times more energy released. So this figure on the bottom is showing you the area of the rupture versus the magnitude. And you can see a magnitude 6 equates to about an area of 100 square kilometers, whereas 10 times larger area equates to about a magnitude 7. So really we're seeing a magnitude 6 to 7 jump, meaning 10 times more energy being released at the fault rupture. Right? So as an illustration, the 1906 San Francisco earthquake was a magnitude 7.9, and that's roughly the surface propagation of the fault rupture compared to the 1960 Chile earthquake, which is the largest magnitude ever recorded, 9.5. So it's about 1.6, a value of 1.6 larger, but that means it's, about 15 or so times larger in terms of energy release. And naturally, you can see the size of the rupture being much larger than the San Francisco. So it's a logarithmic scale, which is very important to note. So it's not just a matter of doubling or increasing it by a certain percentage. It's several orders of magnitude larger. This is quite a nice plot as well. It's showing you the moment magnitude equivalent on the x-axis. So this is kind of the energy released on the y-axis versus our reference kind of earthquake magnitudes that we compare with. So a tornado is kind of equivalent to a magnitude 5 in terms of energy released. The Hiroshima atomic bomb was about an energy at magnitude 6, etc. And you can see this 1960 Chile earthquake is the largest possible earthquake largest earthquake that we've recorded. And really, this is close to the upper bound of earthquakes that could occur. I mean, once we get to the values of 10 and 11, we're kind of at the hypothetical realm and the realm of science fiction here. And so really, we're looking at these orders of magnitudes typical for earthquakes. So that kind of helps us answer, how big can earthquakes be? Well, they depend on the size of the rupture itself and how much displacement is going to occur, but that gives us a natural upper bound in terms of how big an earthquake can be. Now, how often do earthquakes occur? And again, this is, not a straightforward question to answer, but it's a common question I get asked. And we often use what we refer to as the elastic rebound theory to help explain the philosophy behind how earthquakes occur. And this is not a kind of a theory that predicts earthquakes or anything, but it's just a concept that helps us put us in the right frame of mind. So imagine you've built a fence along your backyard, okay? So this is a nice picket fence. However, you didn't realize that the fence actually kind of, or your property sits along an active fault. Okay, so this is a fault, meaning that there's one kind of section of a plate on one side and a section of another plate on the other side. This is several tens of kilometers below the ground. And this is what it might look like once you're finished building your fence. Over several tens or maybe hundreds of years, the fence will slowly move, right? One fault is trying to move up, the other fault is trying to move down. So over time, we're going to see these deformations slowly accumulate. Now, there's been no energy release so far, so it's only slowly moving until at some point the energy that's being concentrated down here is too large to withstand, and there's going to be a sudden release. And that sudden release in energy, or a fling in the energy, is going to cause this rupture. So now there's a clear demarcation or movement of the actual fault, which then causes, in this hypothetical example, your fence to essentially move. Here's an image, by the way, on the right, showing an actual real case where that had happened. But this helps us kind of think of it in the right mindset, in the sense that if we see observations of movement but not a lot of energy release along a fault rupture, that is a sign of bad things to come, because that means that energy is being accumulated slowly over time. And when that energy gets accumulated, it has to be released at some point. Now, when is it released? It's difficult to say, but it will happen, and eventually it'll be released and go to this type of state. So a lack of seismic activity for many decades or centuries is a sign of bad things to come. So here, for example, is a real life example where this is projection of a fault. So this is a very simplified projection of a fault out off the coast of California. And these dots are showing you energy release evidence. So these are seismic activities and microtremors that were observed prior to the Loma Prieta earthquake in 1989. And we can see a large concentration of energy release along the fault here, but then from here onwards, there was a big gap. Okay, and so we're seeing a lot of activity here, but not a lot of activity here. So we're seeing a buildup of energy like this. Now, it's difficult to predict when, but at some point it was going to happen, and eventually it did. In 1989, there was the Loma Prieta earthquake where all of that concentrated energy was eventually released. And so the area of the fault rupture was approximately shown in red here, and you can equate that to then a magnitude using that plot that we were seeing before, which I reproduce here on the right. Okay, and so this gives us an idea that, hey, by the way, when we're seeing these gaps in seismic activity, it's a sign of bad things to come. Right. And that's often why we hear scientists or seismologists talk about the potential for an earthquake is increasing, because we're now slowly adding more and more energy as time passes, which has to be released at some point. Now, we would love to predict when this energy release occurs, right? If we could know it's at this time, at this day, we can prepare accordingly. But predicting earthquakes is a difficult endeavor. And to think about why, it's nice to use an analogy of weather, and this is an analogy that was concocted by Professor Brendan Bradley at the University of Canterbury. I've modified it slightly for the sake of this talk, but let's think about you waking up in the morning, you're going out for the day, and you ask yourself, do I need a jacket today? Okay, that's a natural question one asks when they leave home that day. And I could come back to you as a meteorologist and say, well, I've looked at the temperature data across May, and this was an example concocted on the 21st of May. So I looked at the temperature data, and based on the trends, I can give you a rough estimate and a range of what the temperature might be. So I'm giving you an answer that is statistical, right? This is what we refer to as empirical. It's based on past evidence. And so it's likely to be cold, which may imply rain. So it doesn't even necessarily answer the question, right? We might be interested in rain, but I gave you an answer about temperature. But this is the best I've got. And so you'd be like, well, this is the worst meteorologist I've ever seen. This is the worst weather forecast. I'm just going to bring a jacket just in case. And that's a reasonable way to go, right? So you put the jacket in your car and you go out for the day. However, we're obviously well past this, and we have much better tools, and we use what we now refer to, you can refer to as physics-based prediction, right? So instead of these data sets, we're going to say, well, let's start modeling what's happening with our temperatures, with our humidity, our pressure differences, wind patterns, and let's physically simulate what's going on to make future predictions. And based on that, we may look at, for those in New Zealand, we may then look at Met Service and see, oh, today it's going to be rainy, and these are the temperatures that we would expect, and you go, oh, I'm confident that I need a jacket, or in other days you may be confident that you don't need a jacket, right? And that's because we have the data set to be able to perform these predictions to very, very high accuracy. Now imagine the same analogy for earthquakes. You ask yourself, when is the next big earthquake? We would love to do a physics-based prediction, right? So we would love to be like, okay, this is when the earthquake's going to occur. This is how the waves are going to propagate. This is an example of Christchurch. This is how the waves are going to propagate. This is the areas that are going to be affected. Avoid these areas. Go to these areas. That would be excellent. But unfortunately, we're not quite here yet. And the reason really stems down to two key problems. One is earthquakes happen so infrequently, right? Weather patterns, we have data every second. Okay, and every second of data is valuable. Earthquakes happen every 100 years. And so even to collect 10 data points, you have to wait 1,000 years sometimes. So it's absolutely difficult to try collect data because it happens so infrequently. And it's also difficult to monitor what's happening below the ground. It's much easier to monitor what's above us than what's below us. And so that leads to a lot of challenges, and so we're not quite there yet. And so the best we can do is, again, these empirical estimates where I have to look at data and statistics and say, well, this is the best guess that I have, but obviously there's some uncertainty associated with it. And therefore, our natural response will be, oh, I can't predict earthquakes, so I may as well design for an earthquake just in case. And that's essentially the approach that we're adopting right now as earthquake engineers, is we design just in case. And so often earthquake prediction is given to you in the language of statistics. I know we would like to know when an earthquake is occurring, but we cannot know that. And so instead we say, we give it to you in the language of statistics because it's based on past data and a statistical study. So for example, if we look at New Zealand, the Alpine fault is one of the major faults that leads to the hazards in New Zealand. And so we often, the Alpine fault study looks at Alpine fault earthquakes can be up to a magnitude 8. And remember, it can be less than 8 depending on the area of the rupture. And we say there's a 75% probability in 50 years. This is just based on one of the studies that has been ongoing. And different scientists will give you slightly different numbers based on the latest science or the method that they use. But that's the reason why we often see this in terms of probabilities, is because that's the best we can do. We don't have the physics-based understanding yet. Similarly, for those that are perhaps more familiar with Pacific Northwest, the Cascadia megathrust, which is much closer to my current home city of Vancouver, has an up to magnitude 9 potential, and this one is about a 10 to 30% probability in 50 years, depending on the sources that you use. But again, it's in the language of statistics because that's the best we can do. However, these are not the only faults that play a role, right? So this large fault that occurs here is not the only rupture that could occur and affect Vancouver. And similarly, this is not the only rupture that could affect Christchurch, for example. We have plenty of other faults. So we may be comparing the Alpine fault to, let's say, a Darfield fault, which is smaller, so there's less energy released, but it's much closer. Or we might have the Port Hills fault, which is even smaller, but even closer. And similarly in Vancouver, we have several smaller faults or segment of faults that exist near Vancouver, which may also contribute to the hazard. And so in the language of statistics, we often aggregate the hazard from all of these faults, right? So we consider all of these faults and aggregate all of the hazards and all of the possible known faults and rupture characteristics. The reason why these statistics are always updated is because we're constantly discovering new faults and new rupture propagation paths. And so the more data we collect, the stronger our understanding is of the hazard. But at the end of the day, it's still in the language of statistics. Right. So again, going back to the question, when will my earthquake occur? Well, we cannot predict that, but I can give you some sort of probabilistic estimate. And that's often what you get from a lot of these earthquake prediction models. Now, the final question under the part 1 is how far away from the earthquake is going to be affected? And so naturally, we're asking, hey, if I'm far away enough from an earthquake, am I okay? Right? Is this so-and-so city safe from earthquakes at so-and-so city? And to understand that, we really want to think about what actually affects the shaking at where you're standing right now. And so this kind of computer simulation is a nice illustration of the example. It's a simulation that essentially causes a man-made earthquake. So we're gonna have a kind of a TNT bomb explosion here, which is mimicking an earthquake. And we're gonna see waves travel through the ground, and we're gonna record the ground motion at this triangle. And at the top here, you're gonna see a live recording of the ground motion and how it's being affected. And the key to note here is that while the release of energy here is one big part of the equation, right? The more energy released, the stronger the shaking. You can see that how the waves propagate through the ground, how they then bounce off different layers and eventually reach our site is a very complex phenomena, right? It's not just a matter of how much energy is being released, but it's also a matter of how the waves travel through the ground and get to where we are. And the study of that is extremely important and leads to a lot of complexities, but that's what seismologists and earthquake engineers tend to focus on. Okay, and so to quantify this type of effect, we divide the effects of an earthquake into three pieces. So the earthquake magnitude is really only one piece of the puzzle, right? When we divide the effects of earthquakes, we divide it into three parts. The first is the source, so the actual fault rupture itself. So this can be 10, 20, 100 kilometers into the ground. And this is where things like the rupture area, the length of the slip, the direction of the rupture, energy release, magnitude, all of this plays a role here, right? So this is going to be kind of one of the key inputs that we're going to think about. But of course, once the earthquake occurs, what next? Well, naturally, it's going to travel through the ground towards where we are now. Let's say this is the building that you're sitting in right now. Naturally, we would expect that the further away you are, the smaller the shaking, which is true in general. So this plot here on the bottom is showing you on the x-axis the rupture distance. So as you go from the left to the right, you're getting further and further away from the earthquake. And on the y-axis is one of the measures that we engineers use for the intensity of the shaking. So the higher the number, the larger the shaking intensity. Okay, and you can see that some of these models that we often use suggest that as you go further away, the shaking intensity tends to decrease. And that's true in general, okay? And that's why you often see, right, once you're at several hundreds of kilometers away, the shaking is much less than if you're right next to it. That's unsurprising. However, the site effect is also important. Shaking can still be amplified once again or de-amplified locally depending on the local soil conditions, okay? So just because you're far away from an earthquake doesn't necessarily mean that the shaking won't be high. You could still get local variation due to the specific soil conditions that you're in. A classic example of this was actually the Myanmar earthquake that occurred very recently, magnitude 7.7, and this was a building collapse in Thailand over 1,000 kilometers away. Now, 1,000 kilometers historically has been more than enough for all these earthquake waves to dissipate, but the local site conditions had certain characteristics amplified, which caused this building to collapse. And it was not fully operational building. It was, I think, under construction at the time. But this was a very unique case, and so really it's illustrating the importance of these local side effects, right? These are really going to play a big role in terms of how the shaking is felt at your feet. So it's not just about the earthquake magnitude, but really it's the distance and then the local site conditions. And by the way, we're talking about variations even 100 meters away from one location to another, you could get large differences in performance. Okay, so even within, let's say, the city of Wellington or the city of Vancouver, where I am, even across that city, we're going to get different performances. So with that in mind, we've kind of covered some of the fundamentals of earthquake hazards. Now let's have a look at what the effects of earthquakes are, right? So you can imagine that once we've thought about the earthquake, okay, it's ruptured somewhere wherever my cursor is, it's traveled all the way through the ground, it's gotten to where we are, and now we're going to talk about how we study the effects. And a lot of my work and my Fulbright experience was actually looking at this part of the engineering side. So it's really trying to understand, how does this building respond during an earthquake? How do slender objects, how do water ponds, how do hills and cliffs respond? And so we're going to think about the types of damage that we would expect. And so if we hone in on the types of damage, of course, we would see impacts on structures. The video on the left is from the earthquake in Mexico this year, and you can see the video showing swaying of the building kind of live from the perspective of the cameraman during the earthquake. And so naturally we might see damage along columns or beams or different elements of the building due to the shaking. We might see permanent movement of buildings as well. So you can see here from the Chile earthquake in 2010 and the Kobe, Japan earthquake in 1995, showing some of these effects on buildings. And so these can be quite egregious following an earthquake. Impacts can also be interior. So, for example, non-structural elements. This is actually a teaching classroom at the University of Canterbury, and you can see these non-structural elements also are being damaged. So while this is not a concern in terms of the building's structural integrity, there is still cost associated with repair. And of course, fires and other secondary hazards. So this was an image from Japan. Another famous example is the 1906 San Francisco earthquakes. In fact, if you talk to those that are still alive today from those earthquakes, they talk about it as the San Francisco fires. And they often remember the fires because that was what was damaging more than the actual earthquake. So it can lead to fires, which can be devastating. Effects on hills and cliffs. So we get large faces of hills and cliffs kind of shave off and run down to nearby houses. Rockfall as well is often common, and you can see this house has pretty much been torn in half. Bodies of water, so we're seeing maybe rise in sea level. This was an example from Japan in 2011. The recent earthquakes in Turkey in 2023, there was also a case of flooding occurring after the earthquakes due to changes in the ground. Ponding as well. There's been cases of kind of naturally formed dams as well. That's led to ecological effects on ecological life. So there's a lot of cascading effects from earthquakes as well. Impacts on grounds and services. So here you can see movement of railways, damage to pipes as well. And the phenomena that I study the most, we refer to as liquefaction. It's a very unique phenomena, but during an earthquake, if certain soil conditions are right, it essentially leads to kind of the solid ground beneath you turning into some kind of liquid. And when solid ground turns into liquid, well, what happens to the infrastructure that once sat on it? Well, it's no longer being supported very well, right? So you can see these apartment buildings in Japan, for example, a lot of overturning, and this is all due to this phenomena of liquefaction, right? The ground was once sturdy, now it's behaving like a fluid, and what happens when you put a building on a fluid-like ground? Well, it's naturally going to sink and settle and move. You also get a kind of uplift of buried structures. So buried manholes tend to uplift as well along with the water in the soil. So this is a very, very unique phenomena. And those of you that are from Christchurch will be very familiar with liquefaction because, you know, approximately half of the city was actually affected by it. So a very important issue as well. So now that we have an idea for the types of damage, let's think about seismic design principles. And in this section, really, I want to highlight how do earthquake engineers think when they design a building. So next time you walk into a building in an earthquake-prone region, you'll have an idea for what principles they followed when they designed the building. So remember, we can't predict earthquakes, so we have to design infrastructure for them just in case it occurs, okay? But of course, we can't design them to be infinitely strong. It would be great to have buildings designed such that no matter how big the earthquake, even a magnitude 10, it's going to be fine. And that's just impossible because it's just too costly and resource intensive, right? And so engineers often therefore perform about 2 checks, in some cases 3, and they design their philosophy based on 2 critical checks. The first check is we see what the performance is going to be like during strong and rare shaking events. We refer to this as the ultimate limit state, or the ULS. Okay, so the idea is that we're going to take a very unlikely earthquake scenario, so one that has a very low probability of occurring, but still could, and look at the performance of that case. So, for example, it's approximately about a 2% probability of occurrence in 50 years, or on average occurs every 2,500 years. So we're thinking about earthquakes that occur on average every 2,500 years. And the idea is that we want our buildings to perform in such a way that life safety is still maintained. Okay, so we still want to make sure no one ever dies during any earthquake, especially all modern buildings. However, damage is accepted because the earthquake shaking is just so unlikely, and so therefore probably so large that we would probably accept a little bit of damage and a little bit of downtime for repair. In other words, a little bit of time where the building would be inoperable for repairs to occur. Right, so this is kind of the first check. And so we have tools and methodologies available as engineers to perform these types of checks. Okay, so a lot of my background and my work that I learned during my Fulbright experience was actually to perform these types of checks for several different types of infrastructure. Of course, the second check that we do is then a frequent earthquake shaking. So this we refer to as the serviceability limit state. So this is for service level performance. And this is a much higher probability of occurrence with a return period of around 50 years. In other words, we're expecting an earthquake on average across over lots of time to occur on average every 50 years. In other words, often within its building life cycle. Right? So expected to occur on average once within its life cycle. And during this type of earthquake, we want to design it such that, again, life safety is maintained. Minor damage can still occur, so we may still see some damage to our infrastructure. However, downtime for repair may not necessarily be accepted. For example, if you're designing a hospital, we would want the function to be still operational after some, very frequent earthquakes. Okay, we can't afford for things like hospitals to be inoperable, and so our criteria for performance tends to change. Okay, so it's important to note that the goal is not to predict earthquakes and therefore design for zero movement and zero damage. However, the goal often is instead to definitely have no collapse. So we don't want people to be we want zero death tolls ideally. We want safe evacuation, but we want repairable damage. And so really we're trying to control what's going to occur during an earthquake so that we can maintain this philosophy. So yes, we don't know when earthquakes are going to occur, but we can control how we design our buildings. That part is in our control. And so let's not control nature, let's control what we can, which is our infrastructure. And so that's often the philosophy that's adopted. And so with those two checks in mind, I'll run you through kind of an example scenario of how an engineer might go about to construct a building or any sort of infrastructure that they're dealing with, like pipes, etc. So like I said, we're going to deal with two checks, right? So we're going to deal with our serviceability, so the earthquake that occurs every 50 years, and then our ultimate state, or the earthquake that occurs every 2,500 years. And so on this arrow, I'm showing you the increase in return period. So it occurs every X years, so 50 or 2,500. And this arrow is also indicating that as we go to the right, we're also anticipating the earthquake shaking intensity to be larger, right? Frequent earthquakes probably imply smaller earthquake shaking intensity, whereas these very, very rare events will be much larger in earthquake shaking intensity. Okay, so as we move across from left to right, we're increasing the shaking intensity from small to large. On the vertical axis of this plot, I'm going to plot expected building damage for our whatever building design that we're doing. This is the expected level of damage. And let's say you as a client are interested in designing a building. An engineer might go, well, let's start with our criteria. Well, our criteria is that for these rare events, we want life safety, and damage is accepted. And so the amount of building damage might be somewhere up here. Okay, so anything that's below here, we're okay with, because as long as we maintain those philosophies, we're okay. But these frequent earthquakes that are much smaller in intensity, we only accept minor damage. And so we may have a target design that's somewhere down here. So naturally, we're going to have two different performance criteria. Okay, so in frequent earthquakes, we only want minor damage. In large earthquakes, we're okay with a little bit more damage, but not too much. And so the engineer will start with a concept design, and this is just an illustrative example showing one possible design improvement process. And let's say this is your structure. Engineers have lots of tools, lab tests, experiments, numerical simulations. We do all sorts of studies to then come up with how is this building going to perform. And we may come up with a curve that looks like this. So this is our moment frame. So this is a frame here. And we can see this is what the building is going to respond like. And you can see these circles here sit above the threshold that we're satisfied with. In other words, it's going to damage more during these frequent earthquakes than we would like to. And the same for this large earthquake as well. It's going to damage more than we would like to. This is unacceptable according to many of the building codes around the world. By the way, the philosophy that I'm adopting here is adopted by pretty much every country in terms of building code, with some slight modification, but the overarching approach is the same. The engineer may go back and say, okay, well, let's add these diagonal bracings. This is going to strengthen our building. It's going to resist more earthquake load. Engineers then perform their sophisticated analysis and come up with this curve. And you can see, okay, definitely the damage of the building on the vertical axis has gone down. And you can see in this rare earthquake event, remember, just in case it occurs, we're going to be okay. Okay, we're gonna satisfy the criteria that we have. However, these frequent earthquakes were still above what's required. And so we go back, we reiterate, we may now add a shear wall. Okay, instead of bracing, let's completely add a wall. Of course, it's going to be costly, but that's our requirement. And so now we can see with the shear wall, we've now satisfied both requirements. And so this may be your final design. And so knowing that, when you walk into a building like this, the engineer is designing it so they can control the type of damage that's going to occur. Doesn't mean there's going to be zero damage, but we're trying to control as best we can what's going to occur. And so with that in mind, we'll finish it off with a couple of case studies. So we'll look at Christchurch and Wellington. So just to give context, Wellington is in the lower part of the North Island. Christchurch is on the South Island. And New Zealand is inundated with kind of a lot of seismic activity because of interaction of the Pacific plate and the Australian plate. So there's a large fault boundary that kind of goes along where my cursor is moving. And so cities near this region, like Wellington and Christchurch, inevitably will have earthquakes occur. And so indeed, we observed that in 2010 and 2011, and also in 2016 as well. So let's start with the 2010 and 2011 Canterbury earthquake, which affected Christchurch. So there were multiple earthquake ruptures that occurred in very short time frame, within a year or two. So effects of strong earthquake shaking, relatively large magnitude. So a couple in particular of note, the February 2010 and February 2011 and the September 2010 were magnitude 6 to 7. Remember, these are 10-fold difference in energy release, but we can see what those magnitudes were. And they were very short source to site distances. So there's Christchurch City up there. And so we're located very close to this earthquake. So naturally, we would anticipate the damage to be quite high. So for this particular earthquake scenario, you can see the earthquake source is right here. So this was one of the many tens of earthquakes that occurred in Christchurch. And these are the instruments that were placed in and around Christchurch that recorded the shaking. And of course, unsurprisingly, the shaking is quite high when you're really, really close to the earthquake. So you can see here, the shaking is given in terms of a multiplicative of gravity. So this is saying that 1.6 times gravity of shaking was observed. You can see these spikes are quite high compared to other regions. And as you go further away, in general, it's getting lower. And if we have a look at the earthquake hazard, we don't need to worry about the details of the plot. This is an engineering plot. But the key to compare is these colored lines of what was recorded. So these are these kind of recorded strong motion stations. And then the black line is what engineers tend to design for. And you can see these colored lines are above a couple of these black lines, which suggests that we're close to the ULS level. Okay, so this dashed line is essentially a design spectra that we use at the rare earthquakes. And so this is at the shaking level close to that rare event. And so we know from seismic design philosophy that we should expect damage, right? Because that's what it's designed for. It's designed for life safety, but we should still expect damage. And unsurprisingly, there was a severely affected area in the CBD where about 80% of the buildings were indeed damaged. Okay, so we can see some of the images here, damage to building floors, damage across connections, ceilings and floors, a lot of non-structural elements, parking garages, etc. Okay, and a lot of the damage was not obvious. If when the public was looking at some buildings, they would look at it and say, "Oh, it looks fine," but it had to be demolished. So here's one example where this building was demolished from the outside. It's not very obvious why, but then when you look at the ground movement, you can see these numbers, which are movements of the ground in centimeters, suggesting a large tilt of the building. On the right, again, you can see a large tilt of the building, a couple of degrees, and these are often sufficient to make the building inoperable. Okay, and so about 60,000 properties or buildings were affected in Christchurch, about 40% of the total number, right? Of course, they didn't collapse as we would expect, but there was damage again as we would expect. Many of them were severely damaged and abandoned, and so the total economic loss was in the order of about $40 billion, about 20% of New Zealand's GDP. So so even though they performed according to what the building code said, we're still seeing a lot of effect. In other words, don't expect your earthquake designed buildings to be completely foolproof of damage. And it's going to happen, but it doesn't necessarily mean you're in danger, right? Majority of the damage was due to ground-related issues. There was damage to lifelines and networks, damage to potholes, etc. Lateral movement of the ground relative to buildings. So you can see here this large width that has been formed. This is a crack in quotation marks of 1.6 meters. So the ground here moved 1.6 meters relative to the building, which stayed where it was. Damage of bridge piers and abutments and rotation of these abutments, and a series of other issues that I can go into: liquefaction, retaining walls, piles of buildings, settlement of buildings. So a whole set of issues. But again, we're not surprised that damage occurred because that's what we're expecting from these building codes. Now let's take a look at the Kaikoura earthquake. So on the top left inset here, we can see Wellington City. And then here is Christchurch City. So before we were looking at earthquakes from Christchurch, very close in distance and kind of smaller rupture areas. Whereas the earthquake in 2016, the Kaikoura earthquake, started where this kind of star is and propagated northeast. And you can see the area of the rupture is extremely large, right? So this is a much larger magnitude earthquake. This was a magnitude 7.8. So about 2 magnitudes higher than many of the Christchurch earthquakes, right? So we're talking about 10 to 100 times more energy being released. And Wellington was located about 60 kilometers away from the surface rupture, okay? And so if we zoom in on an aerial map of Wellington City, this is the capital city of New Zealand, these yellow dots are where strong motions were recorded. And if we have a look at the strong motion records, these are only located about 1 kilometer away from each other. So they're within the same city. In fact, they're pretty much all in the CBD, right? We're talking like a 10, 15-minute drive from each other. However, the shaking intensity between these sites was significantly different. Now, you don't need to understand these plots any more than the higher the line, the larger the intensity of shaking. And so you can see here at the point where the black dot is, the shaking intensity was much lower than where the blue dot is, which is again much lower than where that red dot is. So if you're standing where that red dot is, you're going to experience much larger shaking than the black dot. So unsurprisingly, some of the infrastructure in Wellington experienced ground shaking higher than ULS level, but again, due to local site effects. So even though they're all located similar distances apart, local soil conditions can really modify the ground motion quite a lot. And so that's why we see certain buildings perform well, whereas certain buildings don't. Okay, so naturally we would anticipate buildings near this region to perform much worse, and that is indeed what happened. So we saw a lot of damage to non-structural elements, a lot of panels being moved, some of the damage in connections, a lot of masonry structures were also damaged, and movements of grounds and building as well that manifested in the ground like this. And so a lot of this damage was documented. On the left is a very, very complex map, but it gives you an idea of the details that we went into in our research, mapping the cracking patterns of the ground, soil ejecta, which is when soils in the ground manifest on the ground surface, deformations and movements of the ground in the order of several hundreds of millimeters, movements of buildings. On the bottom here, you can see a lot of the land near the edge of the port of Wellington was actually lost. So this was all land that kind of fell into the sea because of the earthquake, right? So we're seeing damage that can be quite egregious due to this level of shaking. And we can aggregate this data and start plotting things like this. So on the right is a typical traffic light plot of the level of damage that we saw on the ground after the earthquake. And so naturally, red means very, very severe, green means very minor, and then orange or yellow means kind of moderate. And so you can see it's a very complex pattern of damage. And this was very, very useful for land use planners and councils. Like you could imagine, if now want to build a building, let's say you want to build a shed for storage, would you rather build it here where my cursor is or build it up here? Well, naturally the second choice, because we expect the earthquake damage to be much smaller. Okay, so we can learn from these earthquakes as well and use that to inform our future land use as well. By the way, before the Kaikoura earthquake, this was the map that they had. This was the best available map, and you can see the entire port is colored in red. And so really land use planners and engineers were going in here thinking, oh, all of the land is equally bad, so it doesn't really matter where we build. We may as well build south because the view is nicer. Okay. Whereas now the latest science and observations suggest, oh, actually there is a big difference, and we know why as well. So we can learn from these earthquakes, even though damage has occurred. We can still learn from them and build plan the future accordingly. So just to conclude and wrap up, earthquake hazards. Where do they occur? Well, primarily near tectonic plate boundaries. So those of you in New Zealand, not be surprised. How big can earthquakes be? Well, it depends on the energy released, right? So the fault size and the slip distance. The larger the fault size, the more energy. When is the next earthquake? Well, we don't know for sure. And the best we can do is make an educated guess based on statistics. And unfortunately, you won't avoid the answer being in a probabilistic term. Okay, it's going to be a probability of rupture, not a prediction. And how far away from the earthquake is going to be affected? Well, the energy of waves dissipate quickly the further you are. So you would anticipate it to be lower, but local site conditions can alter the shaking tremendously. So don't feel like just because you're far away, you may be safe. Really, the local site conditions is important. And so the latest science and technology tries to study this. Designing for earthquakes. Now, we can't predict earthquakes, so we try to control how our infrastructures respond in case they occur. Remember, it's not a prediction, it's just in case. Generally, we always adopt life safety, but damage is unavoidable. So engineers should try control how much, where, and how repairable the damage is. And Christchurch and Wellington are two excellent examples of where, unsurprisingly, damage occurred, because obviously some of the feature of the earthquake shaking was at or above that kind of rare event that we were talking about earlier. Okay, and so when we're reaching those levels, naturally we're going to get damage, which means economic loss as well. Just want to thank once again for your time. Happy to take questions now or happy to answer questions via email if you want to follow up. I'm also happy to provide these slides for anyone that wants to know more. Just want to thank once again Fulbright NZ. Like I said, a lot of this work can be traced back to the early works that I did in Berkeley due to the Fulbright experience. So it's great to be able to contribute this way. Thank you.
Well, thanks, Ribu. Thank you for explaining some really complex concepts in such an accessible way. And we have a question. I'll read that for you. Thanks for the great presentation, Ribu. Just a quick question regarding another limit state in New Zealand named Collapse Avoidance Limit State. How do you think CALS compared to ULS? And is a CALS factor equals 1.5 times ULS reasonable?
Yeah, so excellent question. I can't say for sure whether that approximation is reasonable. I haven't looked at the collapse avoidance limit state. I know of it, but I don't know the details. So I'm not sure exactly. Unfortunately, I can't answer that specific question. But the philosophy of the design for CALS is exactly the same. You're just changing the performance criteria. So I was talking about ULS with certain performance criteria. You can add as many checks as you want, right? You can, for example, many of the geotechnical engineers perform 2 SLS checks, SLS1 and SLS2. And you have performance criteria for them. In the same way, you can add a CALS as well. And it's just an additional performance criteria that's being checked. Unfortunately, I can't answer those specifics because I haven't looked into CALS myself, especially since the seismic hazard was actually updated very recently. So I haven't looked at those details.
The next question, how we can estimate the distance or the place which can be affected due to local site soil?
So local site soil will influence the ground motion everywhere. Okay, so once the earthquake occurs and those waves get to your local area, then it gets amplified or de-amplified and modified as it propagates to the ground. Now, naturally, if you're far away enough, it's dissipated along that path so that the side effects are no longer prevalent. I would have said 5 years ago that maybe 1,000 kilometers is okay, but we just saw recent evidence that maybe even 1,000 kilometers isn't away. What is the upper bound? Honestly, I thought 1,000 kilometers was close to that upper bound. At some point, yes, all the energy would have dissipated, right? An earthquake in Europe is probably not going to affect New Zealand, no matter what type of site conditions you have. So yeah, it's an interplay of those path effects and side effects.
And the last question is, when estimating seismic demand for design, how do we account for the fact that two earthquakes with similar moment magnitude can produce very different levels of shaking at a site because of rupture direction, source to site distance, and local site conditions?
Yeah, so as I highlighted in the talk, moment magnitude is just one piece of the puzzle that we use in our modeling, but we have a lot of other features as well. So if we have a rupture scenario of moment magnitude, we could have two different moment magnitudes that are similar, but if one of them is further away, we're going to use those relationships to suggest that, oh, maybe the shaking would be slightly less, right? And so we would model that accordingly. So when you say how do we account for it, well, we would just say that the further you are away, the less shaking intensity you would expect in general. Now, local site conditions, we can do that through testing, right? So when you go out on site, and let's say you're looking at a building design, you can go out there before the construction and design process, drill some boreholes, perform some tests on your soil, and look at the specific soil profile, and then perform analysis. So you can perform simulations based on your testing to then predict what type of amplification you're going to get or de-amplification you're going to get. So you can do tests at local site level. This is actually why it's extremely important for you not to rely on global models and to really look at site-specific models. And so, every new project at a new building site, you should be performing tests because the local site effects are going to be different from somewhere else. And so that's why you can account for it by basically doing testing and modeling for that specific soil profile.
We have one more question. Is it all right?
Yeah, that's no problem.
Yeah. Right. What further ground improvement methods do you suggest can be done to the reclaimed lands in order to provide more resistance against dynamic loads such as earthquakes?
Yeah, so depends on what you target. So mitigation strategies really depend on what you target. If you're trying to target limited movement, then you can do things like stone columns around the perimeter of the wharf of the port, right? So even if liquefaction occurs and earthquake shaking occurs, if you have a strong and sturdy outer perimeter, it's not going to move out anymore, right? You have kind of this thing to keep it in place. And so if that's your goal, is to minimize movement, that's one strategy. If your goal is to actually limit, water pressures, you might have drainage. There's plenty of other solutions. If your goal is to limit building response, you could do base isolation. So it depends on what you target, and the mitigation is specific to what you want to target. So in the example that I highlighted, they did stone columns because they wanted to limit the movement.
Wonderful. Thank you, Ribu, for your expertise and for your time. And it's so wonderful to have you back with the Fulbright community. Thank you, everyone who joined us today. We hope to see you all at another Good Works webinar soon. Have a great afternoon, everyone. Thanks, Ribu.
Okay, thanks so much, everyone.
Yeah, thanks.